So we've got some additional notes for our permutations. If you want to, this branch of mathematics is called combinatorics, which is a fancy math word for counting complicated and simple things. Some things you count are simple, some are not. And that's where we get permutations and combinations. So for example, oh, I hit to open the wrong one. There we go. Well, while that's opening up, we can still use this one already that we started. We already know the fundamental counting principle, where you make a space for every decision you need to make and put in your number of choices. So what we have to be able to do is to recognize when is it the fundamental counting principle in the question. If you have decisions to make, and each of those decisions has choices, then you can use your fundamental counting principle. Draw a space for each decision. I like to label it underneath and then come up with an answer by multiplying them together. All right, I think the next one is ready. Here we go. So in example 2, we have 3-digit numbers using the 7 digits, 1, 2, 3, 4, 5, 6, 7. It is a fundamental counting principle question, so we can draw our spaces. But now we're talking about what happens if you're allowed to repeat numbers compared to not being allowed to repeat numbers. With repeating the numbers, you could pick any of the 7 numbers first. Does it make sense? You could still pick any of the 7 numbers second and any of the 7 numbers third. And you would get 7 cubed, which is 343. Without repetition, you could pick any of the 7 numbers first, but then you don't know which one you use, but one of them is gone. How many choices do you have now? 6. And then 5. And we also learned that this was equal to 7p3 from before. That's your permutations notation. You have 7 objects, and you are placing 3 of them for permutations. Now, in example 3, we're going to introduce a new strategy, okay? I want you to we're still going to use the numbers 1 to 7, just like before. And the question is saying, how many 3-digit numbers are even? So it's still a decisions question, but what we're going to do is introduce a restriction. You still have 3 decisions to make. What number's first, what number's second, what number's third. And I'm going to go through, don't write this down yet, I'm going to go through a common mistake first and show why it's a common mistake. So if you were using 1, 2, 3, I'm going to even list them out. Just so we can see them all. We're using the numbers 1 to 7. And I'm going to do it wrong to begin with. I'm not going to use the strategy. I'm just going to say, well, how many choices would you have for the first number? You would have 7. I'll do this in red so you know that it's wrong. And then I've used up one number. How many choices do I have for the second number? Any of the 6 could go there. But when I get to the last one and it says that the number is supposed to be even, how many choices do I have there? Well, I look through the numbers 1 to 7. Does it make sense that if it's an even number, you're going to end with either the 2, the 4, or the 6? Right? So does it make sense that I use 3 choices there? So where's the problem? Well, what happens in my 7 if I already picked the 2? If I already picked the 2, then I can't put a 3 here because I don't have 3 choices left. But I don't know if I picked the 2. I might not have picked the 2. I might have picked just odd numbers. So we have a problem here because I don't know what number to write there. Because if I dealt with the first two decisions first, then I might have used up the numbers and I might not have, so I don't know what to write. So what we do instead, what will make sense and what this strategy is if you have a restriction, underneath that decision, write your restriction. Sometimes it's even nice to write out your choices. And if you deal with that first, the first thing I'm going to do is I'm going to pick either the 2, the 4, or the 6 to be here. Guarantees that any of those numbers could be there. But now I go to my first space and make that my second decision. How many choices are left now? 6, because you had 7 numbers, and you used up, you don't know which one, but either the 2, the 4, or the 6 is no longer available. And now you've used up another number. How many choices are left? 5, giving you 90 different numbers using 1 to 7 without repetition and that are even. So this is a new strategy. If you have your fundamental counting principle, but you have a restriction, you need to deal with that restriction first. So I'd like you to try this one. We're still going to use the numbers 1 to 7. And I'm going to introduce you to another new strategy after you do this one in a regular. So I think you can do this one in the way that we just learned. But once you get the answer, I want to see if you can use the previous 2 examples to figure out a different way you could get the same answer. Did you get 120? Deal with the restriction first. This time there'd be 4 choices because it's odd. You've used up a number, leave 6 left, then 5. Can anyone see how they could use the answers in example 2 and example 3 to get 120 as well, but not use this? Nice knowing you. So the second way we could figure this out is another strategy, and I call it the not strategy. And the not strategy looks like this. Sometimes it is very easy to count all of the ways. And do you see that we counted all of the ways in question 2? We found out 7 times 6 times 5. Did we even write it out? No, we should write it out. This is going to be 30 times 7, 210. We figured out that there was 210 in total with no restrictions. And the not strategy, sometimes it's going to be easier to count the bad ones. The bad ones in this case, if you want the odd ones, the bad ones are the even ones. Do you see that we counted that in example 3? So if you take all of them and subtract the bad ones, what are you left with? 120 as well as another strategy. Now in this example, you didn't have to use the not strategy because counting it directly with restrictions is easy enough. But there will be some that using the not strategy is going to be way faster than counting it directly. So it's going to be another key strategy that we're going to use. All right, try this one on you. three-digit number using 0 to 9, and you're not allowed to repeat. Close but not quite. Close but not quite. Close but not quite. Oh, also close but not quite. It is not 987. I'm seeing that a lot. It's not 987 because if it's 0 to 9, that's 10 digits. Ooh, nice, nice. Okay, and it's not 1098. I'm seeing that as well. There is a restriction in this one. What is the restriction? The first spot is not 0. Because last time I checked, is 12 a 3-digit number? No. You gotta, like, this unit, you have to be careful. Because I could have 0 first if I said how many 3-digit codes. If I just change this to codes, it's a totally different question. Because I can get to my garage and push 0 first to get into my garage with a code. Right? Your iPhone, you can put the code, it can start with a 0. It's a code to get into. But as a number, this is not a 3-digit number. This is 12. That's a 2-digit number. So we have a restriction that it's not 0, which means we have 9 choices there. Now, you pick one of the 10 digits, not 0. I mean, you pick from 1 to 9, something to go first. How many choices do you have left? 9, because you had 10. Now 0 can go back in. And you have 9. And then 8 for 648 in total. So the restriction strategy comes up. You have to read the context of the question. Almost every question in this unit is like a problem-solving question. Because if I change one word, the whole question is different now. If it was codes, then it would be 1098. But since it was digits, you can't start with a 0, and now it's 998. So this is where this unit gets a little bit tricky. You really have to read carefully and think about the context of the question. We've also already learned factorial notation, and we can evaluate these without a calculator. How do we get rid of factorials? We always expand the bigger one. So obviously 7 is bigger than 5, so we start using the definition, say, you're going to go all the way down to 1, but as soon as I get to 5, I'm like, I'm going to just stop there and keep the exclamation mark. I mean, I could go 5, 4, 3, 2, 1, and 5, 4, 3, 2, 1. If I really like, if this is like super fun for you, then go all the way down to 1, because you get to cancel out things like crazy. But if you want to save some time, you could just stop there, and then you'll get 42. Second one, start expanding the bigger one. Whoops. 10, then 9, then 8, then 7, and then when I get to 6, I'm like, I have a 6 factorial on the bottom. That'll cancel out. Make sure you add the sound effects. Very important. And then I also have a 4 factorial. If I want to, I can write that 4 times 3 times 2 times 1. If I was doing this with mental math, and I'm going to cancel out, can you see you can cancel out the 8 with the 4 times 2 is 8? Switch colors so we knew what things were canceling with what. I'm also going to, hey, 9 divided by 3, that would leave me with a 3. If I just did all the same colors, you might get lost. So everybody's okay that the 6 factorials cancel out. Then 4 times 2 is 8, so the 8s would cancel out. Then 9 divided by 3 was 3. Now what am I left with? Just a 10, a 3, and a 7, which is 3 times 7 is 21 times 10, 210. So we can do this with mental math. And we can also expand with algebra. With algebra, you have to be careful, because you have to make sure you know which one is bigger. And it gets tricky when they use negative signs. Maybe I should do one of you. You want to do the trick? We'll do this one first, then I'll pick a trickier one. Okay? Obviously, n plus 2 is bigger than n. Okay, so then we start expanding. What's 1 less than n plus 2? It's n plus 1. What's 1 less than n plus 1? You get to n and you're like, hey, wait a minute. Cancel them out. And we're just left with n plus 2 over n plus 1. Where I've seen it be harder for students, okay, we'll add another example. Which one's bigger? Top or bottom? Bottom is bigger. But initially you see the 3 and your brain wants to say 3 is bigger than 1. You have to be careful with that. So the bottom is bigger, so that means we leave the top and we start expanding the bottom. What's 1 less than n minus 1? N minus 2. What's 1 less than n minus 2? N minus 3. And then you would stop and go, cancel them out. And we're left with 1 over n minus 1, n minus 2. So we can simplify our factorials that way. We've learned this already. Permutation is an arrangement where objects, where the order of the objects matter. And when you're doing a permutation, you're only allowed to use something once. So ABC could be ABC and ACB. You could start with a B and go BAC or BCA. You could start with a C and go CAB and CBA. And we could always count our permutations with spaces. And we use factorial signs a lot when we're talking permutations, because you're always going down by 1 once choice has been used up. So you would get 6 ways. Not very hard. We can probably go, there's our formula. This is stuff we've done already, so we're going to go over this a little bit quicker. If you have NPN, right, this is like 5P5. Remember the second number is the spaces? So you have 5 spaces. The first number is the number you start with. If you had 5P5, you should get 5 factorial. Now, interesting thing is in this formula, if I use the formula, I get a 0 factorial in my formula. And we talked about this in class earlier, that by definition we need 0 factorial to equal 1 so that the formula works in all situations. So this is part of the reason why 0 factorial is 1. We can see when we use our spaces that it has to equal 5 factorial. We still want our formula to work, so in this situation, the 0 factorial has to equal 1. All right. Now, if the wind ensemble, I don't think we have wind ensemble anymore. If we just had our band, and they had 10 songs ready, and they were going to play something for the concert, does the order matter? It's like, have you ever been to a concert where they're like, we're going to go with O Canada third? Feel a little bit weird, wouldn't it? Just have like O Canada in the middle of the concert. Sort of like, usually they start with that. If they're going to play that one, it's got to be first. So then, how many different ways? Well, you would have 4 decisions. What song's going to be first? 10 choices. Also be really weird in a concert is if you had 10 songs ready, but you just played one 4 times. That would usually doesn't go over very well. So we're going to assume once you played a song, you're not playing it again. Then you have 9, then 8, then 7. This is the same as 10p4, 4 spaces, starting with a 10. And we get our total, that. Let's see. I might stop there. Oh, math, this is really easy. Okay, I'll stop here. Because I want to give you guys some practice questions. Here we go.